Okay, we did an activity today in class where we estimated the width of the classroom, and then we did some transformations on those observations and observed the impact that it had on the different measures of center and spread and shape. So let's summarize our findings. What is the effect of adding or subtracting a constant, and that we usually refer to that constant as A, from each observation? Well, it will add or subtract the value of A to the measures of center and location. And just reviewing what those are, the measures of center are mean and median. Mode is not really relevant here because mode is for categorical data and we're dealing with quantitative data here. And then location would be the measures such as median, quartile 1, quartile 3, and then also your percentiles are measures of location as well. And what would happen if you add 2 to every observation, for example, making A equal to 2, then all of these values would just go up by 2. So your median would increase by 2, your quartiles would increase by 2. Your percentiles would, and this is kind of confusing for students, but if your 97th percentile was the number 5, for example, it would adjust to the number 7. So adding 2 would have that impact on all of these measures here. But adding or subtracting will not change the measures of spread, such as range, IQR, standard deviation, because it's not really spreading the data out. It's not compressing it, stretching it, that kind of thing. It's just shifting it. So this is just a shift to the right or left in the horizontal axis and does not change the shape of the distribution. So what is the effect of multiplying or dividing each observation by a constant B? And it will multiply or divide. So multiplies or divides measures of center or location by B. And then it does the same thing, I'll just kind of abbreviate it, multiplies or divides measures of spread by the absolute value of B. And it's because if you stretch and you multiply by a -2, for example, it will stretch out your standard deviation, will spread out your data set, essentially, is what will happen. But it won't negate it. So it's always multiplied by the absolute value of B for the measures of spread. Measures of spread must always be positive. So make a little note of that. Always positive, because they measure distances is what they're measuring. This does not change the shape of the distribution, though. So to summarize, if you are adding or subtracting, it changes only the measures of center and location. If you're multiplying or dividing, it changes all of them, center or location, and your measures of spread. But just remember, you're multiplying by the absolute value of B. And y is equal to a plus bx is actually the form that we will use for linear equations in AP Stats when we get to our linear regression unit. And a is just going to be whatever you're adding or subtracting. It's like your constant that you're adding or subtracting. And b is almost like your slope, is what you're multiplying by. And this would, of course, compare to your y is equal to mx plus b in your algebra world, if you will. So you're used to seeing it like this, but this is how we look at it in AP Statistics. And it's all about this unit right here. A is your shift to the left or the right, and B is the stretch or compression that occurs because of the multiplication. So that's how we'll refer to it from now on out. All right, so let's do a little activity here, a little example. In 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. So it's like a flat fee of $2.50 and then $2 per mile. In equation form, fare is equal to $2.50 plus 2 times miles. So you can see This would be your A value here, the $2.50, and then B would be your $2. So putting it in this form here. At the end of a month, a businessman collects all of his taxi cab receipts and analyzes the distribution of fares. So that's how much he actually paid. The distribution was skewed to the right, and the mean of 15.45 and a standard deviation of 10.2 was what he had for his fares. So we want to basically write out this equation. So fare is equal to 2.5 plus 2 times the miles. So essentially, if you knew the miles, you could transform using a linear transformation to create the fare. So you'd multiply the miles by $2, and then you would add $2.50. So it's like a flat fee of $2.50. So the question here is, what are the mean and standard deviation of the lengths of his cab rides in miles? So let's start by solving for miles in this equation. So you're just going to have fare, you'll subtract $2.50, and then you'll divide by 2. And that will give you your miles. So if I want the mean for the miles, I'm essentially going to apply this same formula, but only for the transformation that applies for the mean. And in this case, you know that the mean is adjusted by both the shift to the left and the division by 2, or multiplication by 1/2, however you want to think about it. So the mean for the miles, so I'll just say X bar for the miles is going to be the actual mean for fare. So I'm going to use the mean for fare, which was $15.45. And then I'm going to subtract $2.50, and then I'm going to divide by 2. And in doing so, I will get 6.475 miles. So 6.475 miles. So that is the average or the mean for the miles for this businessman. Okay, now let's do standard deviation for the miles. So the standard deviation for the fares was 10.20. And standard deviation is only impacted by what? It's only impacted by the division. It's not impacted by the shift to the left or right, because this shift to the left is not actually stretching or compressing. It's not changing how spread out the data is. So I'm simply going to divide by 2. And that will give me 5.1 miles. So let's kind of summarize this and see what we have. So if the businessman standardized all the fares, what would be the shape, center, and spread of the distribution? So the shape would still be right skewed. With a mean of 6.475 miles and a standard deviation of 5.1 miles. So you have to think of it as every observation in the distribution. So basically it's all the taxi cab rides that he took. How long were those taxi cab rides? So we're looking at the length of those. And to transform those into fares, we use this equation. So it's almost like working backwards for this one. So we had to solve for miles first to figure out how would you get from fares to miles, and then you do the same exact equation and apply it to the mean and apply it to the standard deviation. So that is how you would basically find the mean and the standard deviation for a transformed distribution. Okay, on to the next page. So what are we even talking about here with density curves? So I want to show you something, and this is something that, let me put a little light on it. This is a little activity I did a couple years ago where I actually collected some data that we thought was approximately normal. And you can see we did a little dot plot. And then if you overlay, this is some high technology here, but if you overlay the curve on top of it, you can see it's not perfect, but if I collected many, many observations, it would begin to take on that form of that curve. That is what a density curve is. So just wanted to kind of show you that little example there. Okay, So a density curve is used when the overall pattern of a large number of observations is so regular that it can be described with a smooth curve. So let's write all that in. A density curve is used when the overall pattern of a large number of observations is so regular that we can describe it with a smooth curve, and this is known as the density curve. So there are some features to the density curve. It's always above or on the horizontal axis. Now, it never actually touches the axis, so let me kind of show you what I mean by that. But it will appear to be on it sometimes, but it can never go below it. So it might look something like this. And it extends on and on and on forever. So my line should also go on and on like that too. But so that's the way it looks. It will never go below the horizontal axis, and that's very, very important. It has an area equal to 1, and that's exactly 1 underneath the curve. So it goes on and on forever. At some point, though, the area underneath the curve is basically 0 for all practical purposes. So certain outcomes that are so extreme would just be impossible to occur or very unlikely to occur. All the probabilities or all the outcomes probabilities are represented under the curve. So it describes the overall pattern of the distribution. So it doesn't have to look approximately normal. It could also be left skewed, right skewed, uniform, all the different distribution shapes we talked about. The area under the curve for any interval of the variable is the proportion of all distributions that fall in that interval. So if you had a histogram and you had your bar here, for example, and again, this is a large number of observations. So the more observations you have, the more all these little gaps will be filled in by these bars, because eventually they get very, very close together in terms of their size, because the intervals get smaller and smaller. But essentially, the area under the curve for any interval is just going to be the proportion of the distribution that falls in that given interval. So think of it like a bar for a histogram. So how can you identify the mean and median of a density curve? It won't always be symmetrical where the mean is basically like the median. So the way we're going to do that is the median is thought of as an equal areas point. That makes sense because the median is splitting the distribution 50-50. However, the mean is thought of as the point at which the curve would balance if made of solid material. So I want you to look, if we don't have time in class, I want you to look at page 83 and page 102 in the book, and that kind of walks you through some examples of that. So this is homework number 2. Complete this tonight, and we'll pick up here tomorrow. Have a great night.